Ladies and gentlemen, today is a really exciting day. We're going to start talking about limits more in depth, which is going to lead us into the wonderful study of that which is calculus. So we're going to be looking at limits, continuity, and convergence. And you better be saying, wait a minute, there's no apostrophe in limits, you fool, and you'd be right. But we're more concerned about with what a limit is than proper punctuation here. Now, don't get me wrong, punctuation is important. But let's dive into our first graph. So right here we have f of x equals x squared minus 1 over x minus 1. And you might be looking at this going, wait a minute, that's a line. That doesn't look right. Well, if you factor the numerator, what happens is it's x plus 1 times x minus 1, and the x minus 1 factor on the denominator cancels with something on the top, making this equivalent to just x minus 1. So this function is equivalent to x plus 1, but remember back here, x cannot equal 1. And you might be going, wait a second, hold on. Where do we see that on the graph? Well, you can't see it because a point is infinitely small, but if we look at a table, look at that, at x equals 1, this function is undefined. So there's a hole in this graph. And what we see here is that as we approach this graph from the left, from over here, as we approach 1, our graph is getting closer and closer and closer to 2. As we approach the graph from the left, we're getting closer and closer to 2, but the function doesn't exist there. The limit there does exist. The limit here, as x approaches 1, of x squared minus 1 over x plus 1 is equal to 2. And we can see that a lot better in the table if we change the settings. So what I'm going to do is I'm going to go to Table, Edit Table Settings, and it doesn't matter what kind of calculator you have, you can do this. And I'm going to start my table at x equals 1, the value that I'm interested in, and I'm going to change my table step to be 0.05. And now you see my table step is much smaller, and we can see that as we approach 1, we're getting closer to 2. From the left is from the smaller values, and also from the bigger values we're approaching 2. And you could change your table step even further and change it to 0.001 to check even more that this limit is approaching, this value, this graph is approaching a value of 2. Our next graph, y equals 2 to the x minus 1 over x. Question here is, what is the limit as x approaches 0 of 2 to the x minus 1 over x? Okay, so we have the graph. We can sketch this graph fairly easily. If you're not sure how, we go Menu, Table, throw in a table here. Now we could very easily plot points, and we see at x equals 0, this graph is undefined. Okay, so what do we do? Well, let's go into our table settings and see if we can't dial in closely what this is. So I'm looking at x equals 0. And I'm going to go 0.01 this time. So what's happening there? Well, it looks like it's getting closer and closer and closer to, can't say 0.7 because, well, 0.7 is down here further. But it looks like it might be getting closer and closer and closer to 0.69. And for now, all we're doing is we're looking at this from a graphical point of view. So we could say that this is equal to 0.69. Let's switch to a piecewise function. F of x equals x minus 3 when x is less than 2. F of x equals x plus 1 when x is greater than 2. Okay, so how do we graph this? Well, this top part, I'll use red for it, has a y-intercept of negative 3. And a slope of 1. And we only use this graph when x is less than 2. So when I get to x equals 2, I'm going to stop plotting points. And it says strictly less since we use an open dot there. The other graph I'll use green for, x plus 1, so it would have a y-intercept there. The slope would go da, da, da. But I start using it when x is 2, and I get this graph. Here's the line, x equals 2, where I'm switching from one graph to the other. So the question here is, what is the limit as x approaches 2 from the positive side of f of x? In other words, as we come this direction on the x-axis, what is the graph getting closer and closer and closer to? Well, that's equal to 3. We can read that off the graph. It's this point right there. That open dot is getting closer and closer and closer to that. The function isn't 3 there, but it's getting really, really close to it. What's the limit as x approaches 2 from the negative side of f of x? So as we come that direction from the left, what is this graph approaching? Well, this graph is approaching negative 1. So as we approach 2 from the left and from the right, we have two different limits. And you can see that, well, the graph is clearly discontinuous here. That graph is not continuous. At 2, there's a jump discontinuity. And that's going to happen when the limits from the left and from the right are different values. So let's make a definition here. The limit of f of x exists as x approaches a real value c if the limit from the left and the limit from the right both equal L, where L is a real number. And then we can say that the limit as x approaches c, no left and right notation anymore, but the limit as x approaches c of f of x is L. Another definition, the line x equals c is a vertical asymptote. We've talked about vertical asymptotes before. But the definition is it's a vertical asymptote of the graph if either the limit as x approaches c from the positive side of f of x is positive or negative infinity, or if the limit of f of x from the negative side of c is plus or minus infinity. And we can see that with the graph of y equals 1 over x squared. We have this curve. It has an asymptote at x equals 0. As we approach 0 from the positive side, of f of x, our graph is going up to infinity and beyond, and we know then that this has a vertical asymptote at x equals 0. And we could have looked and changed this positive to a negative going from this direction, and we see the same thing happening. Now, the definition of continuity. 3 conditions must be met for a graph to be continuous at a particular value. The conditions are 1, f is defined at c. That is, c is an element of the domain for f of x. The limit as x approaches c of f of x exists. And finally, the limit as x approaches c of f of x equals f of c. If those 3 conditions are met, then y equals f of x is continuous at x equals c. And we can sum it up by saying that right there. In the next section, in the next video, we will be starting off with an example examining continuity of graphs.